Hey everyone, welcome to Chem Story. Today we're diving into one of the basic but really important topics in chemistry, electron configuration. In other words, how electrons are arranged inside an atom. It might seem like a small detail, but this concept comes up all the time, whether you're looking at the periodic table or trying to figure out how atoms bond and react. So let's break it down step by step and see how electrons actually fill the atom. First, let's talk about what electron configuration actually means. At its core, it's all about how electrons are arranged in an atom's shells and subshells. You can think of these as orbitals, regions where electrons are most likely to be found. Now, electrons do move, but they're not just randomly scattered around the atom. They follow a specific set of rules that determine where they can exist and how they're distributed based on energy. So electron configuration isn't just a list, it's a map of where electrons are allowed to be and how they're organized inside the atom. To figure out electron configurations, we follow three key rules: the Aufbau Principle, the Pauli exclusion principle, and Hund's rule. Let's start with the Aufbau Principle, also known as the building up principle. This rule explains how electrons fill orbitals in an atom. They do so in a very specific order, based on energy levels. When electrons fill orbitals, they always start with the lowest energy level first. That means electrons move in a sequence, starting from the orbitals that require the least energy and gradually filling higher ones as they go. But how do we figure out which orbitals have higher or lower energy? Well, the energy of an orbital isn't just random, it follows a specific pattern. It's determined by the sum of two quantum numbers, the principal quantum number, n, and the azimuthal quantum number, L. In simple terms, you just add them up, n plus L. And that gives you a way to compare orbital energies. Now here's the rule. If two orbitals have the same n plus L value, the one with the smaller n is lower in energy. So even if the total is the same, a lower n gives you a more stable, lower energy orbital. This is exactly why the 4s orbital fills before the 3d orbital. For 4s, the principal quantum number n is 4, and the azimuthal quantum number L is 0, so n plus L equals 4. For 3d, n is 3 and L is 2, so n plus L equals 5. Since the 4s orbital has a lower n plus L value, it's lower in energy, and that's why it fills before the 3d orbital. Even though it has a higher principal quantum number, the energy rule tells us it comes first. Now, there's a simple trick for figuring out orbital energy levels. It's called the diagonal rule. The diagonal rule is a helpful shortcut for predicting the filling order of atomic orbitals based on their energy levels. Here's how it works. Start by writing out the orbitals in columns. List the principal quantum numbers, 1, 2, 3, and so on, vertically. Then arrange the orbital types, s, p, d, and f, horizontally across the top. So you'll get rows like 1s, 2s, 2p, 3s, and so on. Next, draw diagonal arrows from top to bottom, but moving right to left across the chart. Each arrow should pass through orbitals that belong to a diagonal line. That's the key to figuring out which orbital fills first. These arrows show you the exact order in which orbitals get filled, from lowest energy to highest. So as you follow the pattern, you're basically tracing the path electrons take as they fill up an atom from the ground up. The diagonal rule doesn't replace quantum numbers, but it gives you a quick, visual way to see the big picture. Now let's move on to the Pauli exclusion principle, another key rule in figuring out electron configurations. This principle says that an orbital can hold a maximum of 2 electrons, but there's one important condition: the 2 electrons must have opposite spins, meaning they have to have different spin quantum numbers. So what does that really mean? Simply put, if one electron in an orbital has an upward spin, the second one must have a downward spin. There's another big consequence of this rule. No 2 electrons in the same atom can have the exact same set of quantum numbers. Each electron has its own unique combination of n, L, m sub L, and m sub s. Now let's talk about Hund's rule. This one explains how electrons fill orbitals that have the same energy level, also called degenerate orbitals. According to Hund's rule, electrons will fill each orbital singly first, before they start pairing up. In other words, if multiple orbitals are at the same energy, you put one electron in each before doubling up in any of them. Why do they do that? Because it helps minimize electron repulsion. By spreading out into separate orbitals first, the electrons stay farther apart, and that makes the atom more stable. So in the end, this arrangement helps keep energy lower, which is exactly what electrons want. Let's take a look at how electrons are arranged in the two p orbitals of carbon, nitrogen, and oxygen. You'll notice something right away. At first, each p orbital gets one electron before any pairing happens. That's Hund's rule in action. Electrons spread out across the orbitals singly first, and only after that do they start pairing up. Here's a table showing the electron configurations of elements up to the fourth period, and they all follow the three rules we just talked about. You can refer to the table as I walk you through a few important patterns. Now, let's zoom in on the transition metals in the fourth period. This is where things get a little more interesting. If you take a close look, you'll notice a pattern that doesn't quite follow the typical order. From vanadium to chromium, something unexpected happens. One electron from the 4s orbital moves over to the 3d orbital, so instead of having 4 electrons in 3d, chromium ends up with 5. This shift helps the atom reach a more stable, half-filled d subshell, which is why that electron jumps from 4s to 3d. From nickel to copper, the same kind of shift happens. One electron from the s orbital moves over to the d orbital, and that same principle applies here too. Just like with chromium, copper gains extra stability by filling its d orbital more completely. The d orbital can hold up to 10 electrons, and atoms become more stable when it's either half-filled or fully filled. That's why these elements end up with electron configurations that might look like they're breaking the rules, but really, they're just finding a more stable arrangement. So far, we've talked about electron configurations in neutral atoms. But what happens when atoms gain or lose electrons to form ions? Let's break it down into two cases, cations and anions. When a neutral atom loses electrons, it becomes a cation. In that case, electrons are removed from the highest energy orbital, specifically from the outermost shell, and the number of electrons removed matches the charge of the cation. For example, in the case of a magnesium ion Mg2+, the 2 electrons in the 3s orbital are removed. Now on the flip side, when a neutral atom gains electrons, it forms an anion. Those extra electrons get added to the lowest energy orbital available. And again, the number of electrons added equals the charge of the anion. For example, in the case of a sulfide ion, S2-, 2 electrons are added to the 3p orbital. Alright, that wraps up today's lesson on electron configuration. We looked at how electrons are arranged, the rules behind it, and what changes when atoms become ions. Thanks for tuning in, and I'll see you next time on Chem Story.